everyone. Welcome to another week of 365. We're rapidly approaching the end of the semester, I think. I don't know, there's like, what, month and a half left, something like that. We got to be well past the halfway point. We are doing Computing 101, Assembly. Who's liking this module so far? Is better than crypto? Definitely better than crypto, all right. Who likes x86 more than MIPS? Who likes MIPS more than x86? No one. See, you don't have to.
Nice.
You don't have to withdraw anyone from the class.
Everyone gets to stay.
All right. Okay. So today we're going to focus on some of the ideas in building a web server. So I don't know. Probably most of you are, well, I guess looking at the hacking count, most of you are somewhere in assembly crash course, which is awesome. Continue to learn all these x86 instructions. Another interesting module coming up, though, for many of you will be debugging refresher and building. Oh boy, the camera is just not pointed at me at all. It just gave up. Oh, it just froze also. It has a very interesting facial expression also. All right, we're going to try and unplug this.
Oh, OBS is good.
Is going to lose his mind. No, it's a Mac. It'll work for Mac. Now it's struggling a little bit. Yeah, I don't know if that was Mac to blame there. Okay, the camera's working again. Cool.
You're streaming?
Yeah, we're still streaming. It's a Mac, it works. Okay, so we're going to go over a lot of the concepts in building a web server. And maybe if there's time, we'll go over some of the concepts in debugging refresher. We'll definitely be using GDB throughout this. And then maybe on Wednesday, we'll do more specific GDB stuff, maybe like some GDB scripting or something on Wednesday. But for now, we're going to go into the concepts of building a web server. So last week we wrote, Kitten, and it did this very nice interaction. We wrote it from scratch, made some syscalls. It opened a file, it read the file, it wrote out the file. I think at the very end we had it in a loop where it would like read all the data and then give up, and then it just was a well-formed version of cat minus like -- help and I guess multiple files, and there's more features that you could have added, but it was a kitten, or no, I guess it was puppy.
It was puppy.
It was puppy.
Kitten was in C.
Yeah, it was puppy. So to get to a full cat, I guess.
Next time we should iterate through all the.
Yeah.
That would just be one more while loop.
Yeah, exactly. All right, let's see if we can do that. Actually, yeah. Let's see if we currently still have. I think we do.
No. It was on your stream server.
Was it?
Yeah.
Okay. Let's see here.
Because the dojo wasn't on.
Okay.
Before let's. Yeah. A couple of updates about the module. 97% of the people that started it checkpointed. Yeah. So that's great. Good job. And then we'll keep. You should keep pushing. Don't leave everything to the last weekend. That's gonna be very, very difficult.
I remember some people struggled with building a web server in the past, so I definitely encourage you to not wait for the last minute. I think it's not as bad as crypto, but I know people definitely struggled in the past, so get ahead of it as soon as you can. Okay, so we have this. Let's see here. We have puppy.s that we wrote, and we can see here, kind of looking back at this. I guess at the very end, we figured out where on the stack argv1 was, right? We determined that it was at RSP plus 16 and then dereference it to get the pointer to it. In fact, actually, let's look at that with GDB. Let's just watch it happen to show ourselves we remember how this works. How do I want to do this? We will start up tmux. And we will cat puppy.s. We will GDB, well, actually, before we GDB, let's show that it works. Puppy, flag, and pwn.college comes out. And the very first thing it does, let's see here. Oh boy. Why is this? Here's what we're going to do. Cat puppy.s into less. Can I scroll now? tmux and scrolling. It's always a nightmare. Okay. cat puppy.s. Okay, so the very first thing we do here is this syscall, right? So we basically have everything broken apart into syscall chunks. You should think of this when in building a web server or in this demo, in these kind of simpler programs, all we're doing is we're writing a program that's like making syscalls. Our objective is to make syscalls. And then there's some like simple logic on top of that, like a simple loop. Of course, more advanced programs might do more advanced data manipulation. Ultimately, we are producing this machine, the syscalling machine. Our goal is syscall. So in each of these cases, we'll see we write a block that has a syscall. Syscall, syscall, control flow. This is not a syscall. This makes things interesting. Syscall and then syscall. And as a reminder, if we want to know what syscall is being made, right before the syscall instruction happens, it's whatever the heck is in RAX. So we made it very easy for ourselves to read this program. And so as you write assembly programs, you want to write them to make them easily readable for yourselves. And so probably what you want to do is right before you syscall, you specify what RAX is. Probably in every case in this module, the thing right before your syscall should be a move RAX. Technically, it could be higher up. It could get more complicated. Make it readable, though. Put your move RAX right before your syscall. So move RAX to syscall is, and let me move that there. Syscall number 2 is open. Open takes 3 parameters. We've got RDI, RSI, RDX. Probably you haven't memorized this yet, but maybe by the end of this class, you will memorize the fact that it's RDI, RSI, RDX. This will just be secondhand. You don't have to memorize it. You're always welcome to reference it. But you're going to be doing a lot of syscalls, RDI, RSI, RDX. That's the first 3 parameters. So in the same way that RAX selects the syscall, this determines the arguments to the syscall. So whatever the heck is in RDI should be a file name. And if we look up here, we can see this is where RDI gets set. It gets set to whatever is at RDI. So let's use GDB to, I keep typing kitten. There's too many animals in this class. Puppy. And we will start the program. And we will use some cool features that we previously talked about, like the display thing, which will allow us to constantly see every time the program stops something. And in this case, we're going to have it display 4 instructions at RIP. In this case, we don't like the syntax style. We're going to remember set disassembly flavor intel. And if we want to look at these instructions again, we can always just do that ourselves. You'll learn in this module that GDB is basically a language in and of its own right. So you're kind of simultaneously learning x86 and GDB. GDB might as well be considered a language for your purposes here, right? We got to learn this weird syntax. Not so bad, but you'll get used to it, which says whenever you start with an X, you're dereferencing memory. So dereference memory and print me 4 instructions. As we discussed in the past, I could do print me 4 bytes. Well, I guess this is not bytes. BX would be bytes. So print 4 bytes at this location. Or I could say, instead of X to dereference memory, I could do print as hexadecimal RIP. And this just tells us that RIP is currently 401000. Okay. Let's look ahead and see our syscall. So this right here is maybe something that feels initially unintuitive. What the heck is going on here? GDB is very nice at seeing exactly what's happening. This is why GDB is so cool. I can look at any instruction and fully examine the state of the program. So for example, let's say I want to watch this happen. So we can read this like statically. We can just read these 3 instructions and think in our head, what the heck is this doing? This is putting RSP into RDI. So whatever the current value of RSP is, which is currently this crazy number that got started up by the kernel. The kernel set RSP somewhere for us before it started our program. It gave us a little stack. We'll see that RDI is currently just 0. So hopefully in your head, you know what this single instruction is going to do. You shouldn't even need GDB for this, but you know what? We all make mistakes. GDB is great for confirming. RDI should now be this number after I step. Let's step. And sure enough, RDI is now that value. That was the effect of that instruction. Okay, now we're about to add hex 10 to it. So this thing right here, you should be able to predict in your head. You will run an x86 machine in your brain and understand what's going on here, right? We know that this should now have a 6-0 after I step. Let's step. And sure enough, it is a 6-0. Now this might be the first instruction that you're like trying to reason about in your head, and depending on your familiarity with x86 at this point, you might be struggling slightly more with this one, right? This one's a little more interesting. This one is pulling out of memory. At memory, it's going to pull from RDI. So RDI is specifying where in memory. This keyword pointer thing is like, why is it called keyword pointer? I don't know, historical reasons. Really, it should just say like 8-byte pointer. That'd be a real nice thing to say. But that's what it's saying. It's saying 8-byte pointer. Pull 8 bytes out of RDI. We could also, for example, pull 1 byte. If instead this was a byte pointer, we'd be pulling 1 byte out of RDI. But in this case, pulling 8 bytes out of RDI. And that makes sense because the destination of where it's going to an 8-byte register, right? RDI is an 8-byte register. That thing can hold 8 bytes. So it's good that we're pulling 8 bytes of memory out. There's a question, yeah. Very good question. So the question is this the default? You could write your x86 and just say move space RDI, comma, space bracket RDI without specifying keyword pointer in this case. In this case, that's not always true, but in this case, the size can be inferred because the destination is an 8-byte destination, and that's the only option. You cannot do a byte pointer here and pull 1 byte of memory out and make that go to an 8-byte destination. The sizes have to line up. And so the assembler can infer the size for us. In fact, I think if we'll look after, I think if we look at our source code that we wrote, we might not have even written. Let's see. No. How do I want to do this? We're going to shrink this just to be sure about that. Maybe Jan did be explicit. You could be explicit. You'll see, how did Jan do this? Yeah, you see Jan didn't even write keyword pointer here. You could write it, it would be more explicit, but the destination size is known. If we had this flipped, if instead we were writing into memory, right, pulling, let's say, maybe we put square bracket RDI here, and then just RDI on this side, we kind of reverse the operands, then you would need to specify, because a location in memory is ambiguous of how big that destination is. We might be saying we want to pull 1 byte or 4 bytes or 8 bytes. Hold on, let me confirm what I'm saying is true. Is it ambiguous? If we flip this, would it be ambiguous? Where's the case where it's ambiguous?
So it can be ambiguous
if it's a immediate value.
Yes.
If it's so I think this is what I just said, I think is not true. The test in the audience. If we flip this, I think it's still not ambiguous.
It's
I think
not ambiguous.
Because the source is 8 bytes, so we know we're pulling 8 bytes. The problem would be if we did move square bracket RDI square bracket comma 0, for example. We wanted to put a 0 into that location in memory. Now it's ambiguous because we don't know if that 0 is a 1 byte 0, a 2-byte 0, a 4-byte 0, an 8-byte 0. I think those are really the only options. And that is where you would need to be explicit because you don't know how big 0 is. You might be thinking in your head, well, obviously 0 only takes 1 byte to represent, but what if I wanted to null out 8 bytes? The way the architecture works, or I guess the way the assembler works in this case, is when it's ambiguous, you have to be explicit about it. You could imagine writing your own assembler where it just decides something and resolves the ambiguity by making something up. But the way that this assembler works, ambiguity has to be explicitly stated how big it is. Okay, let's keep rolling then. And let me make sure that when I've been doing full screen, yeah, it looks like that still works. Cool. Okay, so we're about to pull out of memory from RDI. Again, look at this. RDI is this value right here. At memory, if we want to see, let's say, 1 byte of memory, we can use GDB to do that. x/1bx. And what we would say is RDI. And what this means is pull 1 byte out of memory at RDI. This is the GDB way of saying that. And we'll see that it's a null byte. 1 byte at RDI is this. We could do 8 bytes instead. And we'll see these 8 bytes is just all null bytes. And I'm realizing now that how I started this program, we didn't specify a path, and that's going to actually be very important here. So what we should expect to see now that we've printed 8 bytes for ourselves at RDI, is that a 0 should end up in RDI. So currently, as a reminder, RDI is this value. We're pulling 8 bytes of memory out of RDI. After we step through this instruction, because we've already pre-looked at it with GDB, RDI better be equal to 0, unless I'm making everything up and what I'm saying isn't true. Let's find out though. GDB is great at finding reality. And if we print RDI, RDI is now a 0. Cool. This one, easy. 0 going into RSI. RSI is going to be 0. We're not even going to print it for ourselves because we know how move RSI 0 works. It's just going to set RSI to 0. If you're unsure, print RSI, right? You can always print RSI. RSI is definitely 0. And then we're going to set RAX to 2. RAX is 2. And now the interesting thing. The interesting thing is the syscall. The syscall is very cool. And what we're going to do is we're going to step through this, and we're going to investigate the result of the syscall, which is now in RAX. If you ever do a syscall and you see a value like this come back where there's a bunch of Fs, right? We print RAX after a syscall and you see a bunch of Fs. It's not all Fs. Technically, there's a little 2 at the end here. This is a negative number, right? 2's complement. This is a negative number. And what happened here, whenever the syscall returns a negative number into RAX, the syscall failed every single time. Syscall, negative number, basically a bunch of Fs. Syscall failed. So unless you intended for that syscall to fail, something's gone wrong. And if we look ahead, or maybe don't even look ahead, if we think about it, right, what did we put into this syscall? We did RDI, RSI, RDX. All 3 were 0. What syscall did we make? We made the open syscall, which takes a file name, flags, and mode. We just passed a null pointer as our file name. You do this, what file is supposed to be open? I mean, we can go read the man page for man open. So we'll type man open. Obviously, you could do this in your terminal, but we're going to be kind of crazy here and just look at it here. Somewhere in here, I'm sure, right, is going to say, you pass a null pointer as the file name. What's supposed to happen? It's not going to return a good value. And so that is why this syscall just failed. And let me flip this around. And the reason that happened is because the way that I started the program, I started it with no arguments. We could see this also happen with strace. If I do strace /puppy, we'll see actually, in fact, something is very unhappy. We've got an issue here where, there's a bug in our program probably, right? Probably puppy isn't supposed to just spin forever. In fact, we type it without strace and get no output. We'll see we're not getting our terminal back. There's a bug in puppy that I don't think we explored until now. And ultimately, if we do strace puppy, redirect to standard out, and just look at the beginning, we will see right here, this line, exactly as I said, we passed null as the first parameter open, right? Probably you know that this was not your goal. Your goal was not to pass null. And the reason that happened, again, is because we didn't specify an argument. The way we wrote this is that argv1's going there. We don't have an argv1. Instead, we do puppy test like this. We'll see now test correctly is getting passed. It still fails because there's no such file. And probably, in fact, if I do puppy test here, this is going to spin forever because how we wrote this program is it doesn't check errors. It's nowhere in here is it checking errors. It doesn't know the fact that this failed. It just assumed, okay, cool, my file descriptor is -1, and it's going to, well, actually, in this case, -2, and it's going to pass -2 as the file descriptor to read. And then, of course, read is now pissed off because read should have a positive value or 0, right? It should not have a negative file descriptor. So it's mad and it messes up. And then write is completely lost because nothing is doing the error handling, and suddenly we're passing this massive size because this is just whatever the heck is in RDX. This program is just exploding rapidly because nothing makes sense. And it's just constantly trying to read 100 bytes. And if we remember, right, if we look at puppy.s, the check that we tried to implement here for when we stop spinning is we have this test rex jump 0 done. And this is basically just checking if it's 0. So if it's 0, we're done. But what's happening is every time we're reading, we're getting a negative number. And so the negative number is showing up and it's not 0 and it's spinning forever and it's never going to end. So that's what's going on there. Does anyone have any questions so far, whether it's GDB or x86 or anything I've said so far that makes no sense? Because this is about to be your life on building a web server, is like living and dying by GDB.
I guess I have a question.
Yeah.
How would students put in expected return values? Like, you kind of expect that every syscall succeeds.
Yeah.
Is there a way to check that?
Yeah, so we could check to see if every syscall succeeds. And what we're going to do is check to see if the return value is ever negative. If we ever do a syscall and the return value is negative, now we're in an error state. And you could write your program. It's up to you how you write your program. What should happen when a syscall fails? You might say, put out an error message saying, hey, the open syscall failed. Or you might just decide to exit with a error code of 1. Or, it's up to whatever the heck this implementation is supposed to look like. So let's see here. Do I have Emacs? We do have Emacs. Very cool. But my Emacs, something is a disaster. Why can't I? Whatever, we'll roll with this. What we would do, for example, is right here, right after this syscall, we have a return value in RAX. We want to check to see, is this errored, right? We want to check now, is RAX negative? And one way we could do that, let's see here. I personally don't like the test instruction. I have a vendetta against the test instruction because every time someone writes a test instruction, I have to start thinking, what the heck is a test instruction? I like the compare instruction personally. And so what I'm going to do is I'm going to compare, if you like the test instruction, go ahead and use the test instruction. I think the compare instruction makes more sense. The reason you see a lot of crazy things like test rex, this insane line, is literally just because it takes less bytes. So GCC will emit something like test rex, because GCC knows what it's doing and can get it done with less bytes of instruction. Turns out people really like smaller programs, and that's ultimately why you see this terrible code. But we don't care about the size of our binary right now, or how big a single instruction is. So we're just going to compare RAX with 0. And we are really sad about Emacs. Emacs is very upset that this isn't all indented because this is badly formatted assembly, but we'll keep rolling with it. And what we're going to do is we're just going to say jump less than. We could also do jump less than or equal if we wanted to include the 0 case. We're just going to do jump less than, because if you compare RAX with 0, and it's less than, right? If the answer is that it's less than, it's a negative number, right? So jump less than, and we're just going to type error for now. And now we need to figure out where the heck error is. We're just going to put error at the very end. Probably there's all sorts of ways you could imagine writing this. Maybe we really just want to jump to done and put RDI in a value, and now this thing's not in control of RDI. You got options for how you write this, but we're going to do this in the dumbest possible way. Nice and simple. We'll have code duplication. The error state is going to move RDI, and we're just going to put 1. This is a common convention for an error, is that your program returns something other than 0. Normally, the convention says not 0, that's an error. And so that's the convention we're going to follow. We're going to move RAX 60. Again, why 60? Well, maybe we know that this was our exit call from before. We could double check that though. If we search for 60 right here, this is exit. We're specifying our error code. Again, convention says that a 0 exit code is a clean exit. A not 0 exit code is bad. You could make up your own convention, I guess, if you wanted to, but the rest of the world says this is the convention.
For programs.
For programs, yeah, exactly.
For functions is the opposite.
Yeah, for fun, exactly. Very, very fun. I guess basically probably the convention is that way because you might want to have different error conditions, right? There's only one thing that is good. And so we'll just say 0 is good. And then there's multiple ways of being bad. So you give all the other values bad. It's probably why they did it. And then we syscall. So as a reminder, we added this error state. This is just a label. Now we can jump to this label. And we added a compare RAX 0 jump less than error right after the syscall. And in fact, we could put this after every single syscall if we want, because we will never want a syscall to return a negative number. There might be times where your program is totally cool with a syscall returning a negative number. For example, maybe you're opening a file, and if that file fails to open, you want to notice that, and you have a fallback file. You're like, well, this file doesn't exist, so now I'm going to go try this file, and then I'll try this file and this file. You might have written a program that takes in a config, for example, and it's going to try like 7 locations. And so you write your control flow to account for that. In this case, our program is nice and simple, no bad syscalls. Okay, let's reassemble this. Okay, right, assemble it, produce the object file, link it, produce the actual runnable. We got our warning, we don't care about our warning. And now if we run puppy, it exits, right? We'll see here. We see it gets a negative number, and we exit with 1, right? We could also check echo $? It returned a 1. However, if we do puppy /flag, it returned 0. So now we know, right? You just think of this as like programs working with programs working with programs. You might have a program that wants to call puppy and then check to see if it failed or succeeded, and it's going to check its exit code. And that's kind of what's going on there. Again, any questions so far? Does anyone have any questions? This is going to be your life in building a web server. Everything I'm doing, and you hit a problem and you're confused, everything I've done so far, this is how you're going to get through that problem. No questions. We'll keep rolling then.
I will keep rolling. I got to run.
Yeah.
All right. Good luck.
Yep. See ya. Yeah, Jan has to run early today.
Picking up baby Jan from preschool. Keep the scheduling mix up.
All right, we'll keep rolling then. So let's go ahead and how do we want to take this? Yeah, let's keep editing puppy. So currently our puppy program does all of this, right? And actually, now that we have it working, let's again show. Let's go ahead and show this instruction again. Before, the first time we ran it with GDB, we saw null bytes going in and RDI was going to 0 and then everything was failing. Let's start it correctly by specifying a path that exists and watch what happens when it actually succeeds. Let's do GDB /puppy. We'll do start I and we'll specify an argv1. So this is the way in GDB that you can specify argvs. So start I /flag. We'll just say no to that, and we'll do our set disassembly flavor intel, and we'll do display for I RIP, and that's probably good enough for now. Okay, let's just step, and we're back to this instruction. Again, if I want to look at what the heck is RDI, and I want to print 8 bytes at RDI, because this is I'm trying to like confirm everything, right? I'm writing a program and there's been bugs and I want to double check that I don't have a bug and everything's working as I expect it to work. I'm going to use GDB to do that. I am going to print out 8 bytes here. And we'll see now it is not null bytes, right? It's this crazy E3, E5, FF, 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 7F, 0000, right? These are the 8 bytes at RDI. And this might look maybe in some ways worse to you than a bunch of null bytes. You're like, what the heck is E3 and E5? Don't panic. This is, if we want to look at it a different way, we could print it as an 8-byte value, x/gx. I know this syntax is terrible. I wish it was like dereference 8 bytes at this address. You can just type English. The GDB syntax is a little arcane, but you're going to get used to it. If we do this, now we can see it's this. And maybe this looks a little more reassuring. This is a pointer. This is a pointer to the stack. As you continue throughout this class between this current module, the reverse engineering module, eventually the memory corruption module, you're going to get very comfortable with raw bytes. You're going to get this intuitive sense that if you ever see, so before I said if you ever see like a bunch of FFFFFFF, that it's a negative number, and if that comes after a syscall, that's bad, probably. In this case, we have some zeros and then a 7F, FFFFF. You ever see something that looks like this? This is going to be a stack address. 7F, FFFF. This is the stack. Okay, so, and we could even know that it's a stack. For example, if I print RSP, which is the stack pointer, these things aren't exactly the same, but they look pretty similar, right? This is the stack. If I want one more way of getting an intuitive sense for this, I can do, let's see here, info proc maps. See, even sometimes I have to think about this arcane GDB syntax. Nope, info proc map, not maps, map. Info proc map. This is going to give us information about the process, and it's going to look at the memory maps. That's what this all translates into. And this right here is all of the memory allocated to our program. If we ever reference a pointer and try and dereference it, and it's not in this range, so for example, from 400000 through 401000, right? It has a size of hex 1000. This is one page of memory. This is another page of memory. This is 4 pages of memory, right? So 4000. Page of memory is size hex 1000. 4 of these, that's 4 pages. If you ever have a pointer that is not inside of one of these ranges, that's a segmentation fault. If you've ever seen seg faults, right? You wrote a C program, for example, and you accidentally dereference a null pointer. That's because guess what? Null is not defined in here. There's no address that's valid between here. There's actually ways to define the null page. And if you define the null page, you need some permissions to do it, and we're not going to do it here. But if, for example, and it's very unstandard to do this, but if you defined the null page, all of those null pointer errors would no longer be null pointer errors. It would just pull from the null address. Again, you need some special privileges to do that. It doesn't really matter for us, but that's what's going on. Segmentation fault always means you got this memory allocated to you. You're dereferencing memory somewhere else. Okay, and as I said before, we have the 7FFFFF thing, and that right here is in the stack. Okay, our size of our stack is currently 21 pages. The stack is willing to grow. There's reasons that the stack might need to grow, right? You start using more space, the stack size is willing to grow. The kernel will take care of this. But ultimately, we have a pointer in here pointing to it. Okay, as a reminder, taking a step back, the open syscall, which is what we're currently setting up for, takes this file name pointer. The file name pointer needs to go into RDI. We just set RDI, or actually, I don't think we technically stepped through this instruction. Let's even step, right? So we're expecting RDI, which is currently equal to 0. Nope, just kidding. Is currently equal to this. Remember, the previous instruction did something with RSP and then increased it by hex 10. Let's pull out of memory. What we're pulling out of memory is this thing, right? These look similar. They are different values, though. If we understand how this instruction works, RDI is now going to have this value. Let's step. Let's print RDI, and sure enough, it has this value. Okay, we've got 2 more instructions and then the syscall, and neither of these instructions mess with RDI. We just set RDI going into this syscall. We just set the file name. It is a pointer. You've written C before. You know what a pointer is in terms of like this visualization, right? Where we have car star, the star, right, being a pointer. This is a pointer. This does not look like /flag, right? This doesn't look like /flag. But at RDI, so if we use RDI to reference memory, if, for example, we pull 1 byte of memory right from here, guess what that is? That's a 2F. Does anyone remember from web security what a 2F is? No one's remembering 2F. Yeah. It's not a space, so a space is 20. Good guess, though. It's very close. 2F. Not quite. So 2F is a slash. Oh, wait, I see hands. Yep. It's a slash, exactly. 2F is a slash. Again, I'm like saying this like you need to memorize this. You don't need to memorize this. It's totally fine if you didn't know that. As you do this more and more, just like this sort of knowledge just bakes into your brain because you have seen the 2F a million times. We could also use GDB to kind of more nicely show us. Instead of saying I want 1 byte as a hexadecimal character, I can say I want 1 byte as a character. And we will see that it says, sure enough, it is a slash character. We could look at 1 character at the next address. So currently we're looking at 5E3. Let's look at 5E4, the byte sequentially right after it. It's an F. And then an L, and then an A, and then a G, and who knows what the next byte's going to be? Does anyone know what the next byte is going to be here when I type this 8? Curly brace? Not quite. So this is our path. Yeah, I heard someone say null. It is going to be a null byte. So there's kind of 2 ways when you're referencing memory that are pretty common. And you're basically, there's this question, right? You reference memory, and when you're referencing memory, in some sense, you're pointing at just like 1 byte. But you're not necessarily, you're pointing at like the start of some sequence of memory, right? And that sequence of memory might be 1 byte in size. It might be 20 bytes in size. It could be 7,000 bytes in size. And there's kind of 2 ways to represent the size, right? Really, in some sense, a pointer is just a location in memory. But normally when you're dealing with a pointer to memory, there's 2 things you're interested in: the location and how many bytes we're talking about. There's 2 common ways to do that. One is to give a pointer followed by a size. You've probably seen this in C. There's certain APIs, for example, like if you write memcopy, right? Memcopy is going to take a location, it's going to take a pointer, and also how many bytes are we talking about. But there's also kind of the very similar to memcopy, but a little bit different, is strcpy. And in that case, you don't actually pass around a size. You just say it's here and keep going until you see a null byte. Okay, paths in this case follow this null byte convention, right? And that's because basically the kernel decided it's totally cool. You don't get to have a path with a null byte somewhere in the middle. Whereas if you think about something like memcopy, right, you might be copying 20 null bytes off to somewhere. You can't use this null byte trick of just go until the null byte, right? These are 2 very related things, slightly different. That's really important. And they have different performance gains, right? If you think about like 310, for example, CSE310, data structures, algorithms, if you pass around the size, it's O of 1 complexity to know the size, because guess what? You just got it passed to you. If you don't pass around the size and you pass around this thing that ends in a null byte, if you want to ask the question of how big is this thing, you got to walk all of memory until you get to the null byte, right? There's data structure considerations here. But it's simple enough, and in the case of something like a path's not going to be so long, right? The path is not going to be more than like 256 bytes, right? Probably. It's going to be a pretty small thing. If you have to walk memory to find the null byte, it's not the end of the world. And ultimately, open uses this convention. If we look at read instead, right? So I just said, this is the null byte guy. Read and write are the other style, right? A location and a size. And the reason for that is you might read in null byte and you might write out null bytes. You can't use this like null byte to mean something. So that's kind of like a little bit of something to think about a little bit, right? 2 standard paradigms here of talking about memory. One is the C string thing, ends in a null byte. The other is pass around the location and the size. Both very common, both have trade-offs. Okay. And so now we've specified RDI, which is a pointer to these bytes in memory. So the kernel is going to read from memory and see that we're talking about /FLAG null bytes. And it's going to try and find that on the file system doing its kernel things. And it knows the file system. And you don't have to worry about how the kernel does it. But the kernel is also just x86 assembly running at the end of the day. Interesting little thing to think about. And then we have our second argument. Second argument is RSI. We're thinking about the second argument. This is flags. So we're passing whatever the heck flags are, and we can read the man page. It talks all about these flags. There's like O append, O async, O clo exec. All these things mean different things. That's the flags, and we're just passing 0. Turns out 0 means read only. So we're opening the file read only. And if you wanted to know, there's a good question that I'm preemptively assuming, how do I know that 0 is read only? If I read this man page, it's going to talk all about O read only. But I'm not going to do it here. Nowhere in this man page does it say O read only is the number 0. These two things are identical. O read only just means 0. Okay? But the man page doesn't talk about it. It's very sad. It'd be cool if the man page talks about the fact that O read only is 0. There's another one, O read writes. This also just has a number associated with it. And also the man page doesn't say what number O read write is. Here is how we can figure that out. Let's minimize this for our quick little side tangent. It will become very relevant in building a web server. You need to be able to figure out these constants and what their numbers are. Okay, here's how I like to do it. There's like 20 different ways to do it. This is my favorite one. Inside of the file system, there is this directory called user include. Okay, you're probably pretty familiar with user include, and the reason you're familiar with it, if you start looking at this, right? Standard lib.h exists and string.h exists. These are all things you've like pound included in a C file before when you've written C. When you pound include, it is just looking at user include by default, user include / whatever the heck thing is that you specified here. And what these header files specify is what the values of these constants are. Okay, so user include is on the user space side of things, and your C program, when you specify in all caps O underscore read only, pulling in from that header file the fact that O read only is a 0, there's probably somewhere in there a pound define O read only 0. Turns out that is definitely true. If I grep through user include for O read only, here is every location on the file system that references O read only, and we will see define O read only 0. This is the best way to do it. Unfortunately, no one has, at least that I know of. The man page doesn't save these values. There's not like a x64.syscall.sh, but like what are all the constants? Maybe like constants.sh. Maybe you want to create that website. That'd be a cool website to point people at. The simple thing is to just do what GCC does when you do a pound include and follow its logic. At least that's the style I like. Pound define O read only is a 0. And in fact, if you wanted to be more specific, generally this will work out for you. You can grep specifically for pound define O read only. And now you might ask the question of, well, what is read writes? Read write is 2. And what is another one of the flags? O create. It is this. You'll notice also that it starts with all of these zeros. This is octal. Okay, just for some reason someone decided that they want to define these in octal. That's fine. We can deal with that, but this is how you find those values. And so ultimately we're passing 0 there. And then there's that third thing to open, the mode. If we print RDX, that's also 0. Turns out the mode doesn't matter for us. Like, there's lots of things to refer to. It's like user include is what are the values. The man page talks about how everything works. If I search for mode in here, it says here, the argument flags must include one of the following access modes. Read only, read write. This is a different mode than what they're talking about. We could keep reading. Keep reading somewhere in here. This right here, yeah. It's basically, if you do ocreate lets you create a file on opening, and the question that the kernel is going to immediately ask you is, well, what permissions should this new file have? That's what the mode is. The mode just deals with Do I want the user to be able to read it? Do I want other to be able to read it? All of that sort of thing. And that's what the mode is. You only need it for creating the file. So we set 0 because it doesn't matter. I actually am not sure if the kernel would yell at us if we set it to something or if it would just silently ignore it. You could test it if you wanted to. It doesn't really matter for us. I guess unless we got an error, in which case we'd see the mode is something other than 0, and maybe we should be safe and set it to 0. And so ultimately, let's see here, where are we? We're setting RSI to 0. Okay, we set that. We're setting RAX to 2. Now we're about to do a syscall. We set up RAX, which is selecting our syscall. We set up RDI, RSI, RDX, which are our arguments. And the result comes back in RAX. It returned 3. You might be thinking, why 3? Well, first thing you should be thinking is it's not a negative number, which is very cool. That means it didn't error. Why 3? Well, because as Open talks about in here, where does it talk about it? Let's see if I search for return. Yeah, there we go. The return value of open is a file descriptor, a small non-negative integer that is an index to an entry in the processes table of open file descriptors. Ultimately, this is just a number that you're going to reference later on whenever something is asking for an FD. So for example, read wants to know what file to read from. You reference that file that you're going to read from through a file descriptor. The way you get a file descriptor is you open a file. You open the file, you get a file descriptor, and now you can read from it using the read system call. Turns out open is not the only thing that will return a file descriptor. There are other things that will return a file descriptor. So for example, kind of a boring one, but there's also the open at system call, which is very similar to open, but has this extra first argument, kind of shifts all the arguments by 1, and it has this. This open at system call lets you open a file relative to another directory. So by default, you're kind of always opening things relative to the current working directory. And so that's what open kind of implicitly uses here. But open at would allow you to do something where you open, let's say like /etc. You open that, which you can open. You can open a directory. There's nothing stopping you from opening a directory. You might be thinking to yourself, like, why would I do that? Well, this might be one place you would do that for. So I could open /etc, get a file descriptor, and then pass that file descriptor to open at, and then I might say a file name of password, PASSWD. And now it's going to open password relative to etc. And that's the behavior of that. And the reason I know that is I've read the man page for open at. And this will talk about that. Who the heck is that? Ad served by Google. Yeah, so that's what's going on here. We don't need to care about this, right? This is just another system call. There's a lot of system calls, right? There's 332 of them according to this person. You're not going to learn all of them here, but you're going to learn a few of them. So open returns a file descriptor. Open at returns a file descriptor. In building a web server, you're going to use the socket system call. The socket system call is how you start doing networking stuff. If you want to start talking TCP, for example, you are going to do the socket system call. And so in building a web server, watch the lecture videos. I'll talk all about the socket system call. You're going to use the socket system call. And that, as it turns out, if we read man socket, and we search Control F for return, and yep, I guess it's the very first sentence. Socket creates an endpoint for communication and returns a file descriptor. So you could, for example, call socket, and that is going to return to you a file descriptor. And then ultimately what you're actually going to end up doing is reading from. It's not necessarily that you're reading immediately from it. You'll see in building a web server, there's a few more system calls you're going to make. Turns out at some point you'll make the accept system call. And the accept system call, here we go. Guess what? The accept system call returns a new file descriptor. Everything's just returning file descriptors, at least that we're looking at. Accept returns a file descriptor. And the accept system call deals with finally receiving a connection. When someone connects up to you, you accept their connection, it returns a file descriptor. And if you want to read what they said to you, now you can just use the read system call. So it's kind of nice. These file descriptors, a lot of system calls emits a file descriptor that means this thing is now readable and writable. It's kind of nice because the open system call deals with files on your file system. The accept system call deals with, for example, a TCP connection. And then ultimately you can just read and write from these things because they just take file descriptors, and it's a very nice setup. Okay, taking a step back, any questions so far on anything I've said? I know I've said a lot, but this is it's gonna be your life building a web server here. Not seeing any questions. Okay, let's do what we set out to do maybe at the beginning of class here. We talked about how, very briefly, we talked about how, for example, cat flag can take multiple arguments, right? We can do cat flag flag. This is just a problem of control flow, right? We're going to be writing some control flow that is going to be walking over argv and doing our current puppy operation, right? Puppy slash flag, it's happy to print 1. Of course, right now, there's no logic in there. There's no control flow to handle the idea of, well, what if there's more arguments? We didn't implement that. It's just not baked into our program. If we want to handle this, this is just a loop, right? We need a loop somehow. We want to do the current logic of puppy that works against argv1, but also make it go against argv2. And then if there's argv3, right, cat can take a whole bunch of things. You could also throw an etsy password in there. And then another flag, right? The whole point of cat, normally you're just passing one argument to cat, is outputting it. The reason it's called cat, for those of you that don't know, is for concatenate. This is actually what cat does, is it concatenates files together. But obviously, most people just use cat to print out one file, so that's why they're like, why the heck is this named after like an animal? It's concatenate. That's really what cat is. And currently, puppy, well, not slash cat, does not do this. So if we want to add this, it's just a problem of control flow and figuring out where is argv2, where is argv3, where is argv4, and then also figuring out how do we know how many arguments there are. Okay, so let's go ahead and let's actually figure this out with GDB. Let's, if we do GDB./puppy, and we do set disassembly flavor intel, and we do display 8i RIP, and it says nothing's there, but then we start I on /flag, and then we'll do A, B, C, D, E, F, and let's see if we can find these things in memory. Okay. Cool. Okay, so we know that this is about to successfully find /flag. And ultimately, it's going to take RSP. It's going to do RSP plus 10, which, again, I guess maybe not again. GDB lets you add things together. It's kind of convenient, right? I can do RSP plus 10. I can start like predicting what the program is about to do and start reasoning about it before the instructions take care of it. Kind of nice. And then ultimately, it's going to dereference it. So, well, we'll keep it simple. Let's just take this address now. And I can do x/s to print it as a string. That'll follow that logic of just go until a null bytes. X/s will do the whole null byte thing. And we can see somewhere in here I messed up. I messed up because it's a pointer to a pointer, right? argv, if you've written a C program, it's ** or *argv bracket. It's a double pointer. If I want to figure out what is here, what the? Hold on. RSP. Oh, I'm doing very fun mistake to make. I am doing decimal 10. We know though that it's doing hex 10. Okay, so we want to see what is at this address. At this address is a pointer. And then at this thing is /flag. Okay, so the question then is, well, where the heck is, what else did I pass? ABC. Where is that guy? Where's DEF? Maybe where's argc? I need to figure out where the heck is my data so that I can start doing control flowy things using this data. Okay. So I think we kind of showed this on Wednesday. Let's double check though. That if we look at, instead of plus hex 10, if we do plus 8, maybe plus 0. Thought it was going to be there. Here's what I'm going to do. I legitimately do not know where argc is or argv. I have an idea of where it is, but I truly don't know the answer to this question. We're going to use GDB to answer this question. Here's what we're going to do. We're going to take the stack, and we're just going to print a whole bunch of data on the stack, 100 GX. Okay, so it looks like at the top of the stack, or right at the start of RSP, let's say, is the number 4. So probably that is where argc is, because 4 sounds like what argc would be. And I think we showed last week that that is in fact. And then we decided that this is argv in here. We could see even more, right? So this is a bunch of our stack. We just like dumped a bunch of the stack and we're just looking at it. So we have this 4 here, and then we have this E5DB guy here. So let's look for E5D0. And you'll see right in here is like a whole bunch of ASCII. So let's just roll with this then. Right, the whole bunch of ASCII is in here. And for example, if I wanted to like see all this ASCII and I wanted to, we could print 100 strings starting at this address, and we'll see all of this data, right, in here and here. And just keep going. We've got the environment in here. And then eventually GDB starts yelling at us saying memory is not mapped here. This is like almost the equivalent of a seg fault, except GDB doesn't crash. It's just like, no, you can't go there. And so we can see all of this stuff is on the stack. Now we've got to play a game of how do we reference it. I've got a good feeling here that we saw here that at RSP plus 16, so at RSP plus 16, which is this guy right here, right? This is plus 0, plus 8, plus 16. This guy right here was slash flag. Got a good feeling that maybe the next guy is our next argument. Let's see. Yep, ABC. And then this guy right here is DEF. And then it's null. Okay, so this is when I talked about how you're referencing memory and you're either going to include a size or you're going to be null terminated. This is not just true of C strings. C strings are definitely one place where you use null termination to represent like a path, for example. If you think back to C, maybe you remember argv ends with a null pointer. So it's not just, again, it's not just like C strings that end with nulls. You can also end with a null pointer. Now, in this case, we're doing both styles, right? So this 4 is the size, right? So I told you you can pass location plus size. argv, I guess, how the kernel sets everything up for us, all of this data just showed up from the kernel. argv is doing both, right? It's kind of redundant. You don't need both, you just need one. It's both telling you the size, which is saying there's 4 things, and here's the first thing. This is the program name. This is argv1, argv2, argv3, and then it also null terminates. It just did them both. Maybe some people want to walk until a null pointer. Maybe some people want to pre-know the size. It decided to do them both. So what we'll do is, I don't know, we could pick either way, right? Ultimately, what we need to do is loop through all of our arguments. We could choose to, so we want to start at argv1, right? We're skipping argv0. We're not trying to output argv0. That's just our program name. For the purposes of our program, we don't care about the program name. argv1, though, we do care about, and that's what we're currently outputting. We can either start walking these pointers until we get to a null pointer, or we can just use this thing. Either implementation is going to work just as well. Let's go ahead and let's just use argc. I like argc. Okay. So we have discovered that argc is right at RSP. argv1 is at RSP plus 16. Before we start writing this, does anyone have any confusion or questions about what I'm saying, right? It's critical that we know where the data is before we start using the data and that we understand this. I'm not seeing any questions. Very okay. Hopefully that means everyone understands. I can quickly check the Twitch chat maybe, see if there's questions. No, it looks like there's discussions going on in here, but no one has a question. Okay. So we're going to, in our heads, we're thinking about what this program is going to look like. We're going to turn that into x86. You've done this. You've thought about what a program should look like, and you've turned it into C, or you've turned it into Python, or turned it into Java. Just doing the same thing. We're thinking through. Okay, at RSP is argc. What we're going to do is immediately decrement argc by 1. And the reason we're going to do that is because we don't care about this guy, right? So there's only 3 things. If argc is 4, there's 3 things we want to look at. We want to look at this, want to look at this, look at this. We can think about the edge case, or not the edge case, the default case that we were initially implementing for is where it's just one thing. And argc would be 2, right? It would be 2, and we just start here. Instead, it's 4. We got 3 things to go over, okay? We're just going to control flow for that, right? Take this, put it in a register, decrement it immediately. So just take from RSP, pull out of memory, pull that number into a register, sub that register by 1. Now we have how many things we're going to go to. Then set some register to RSP plus 16. Okay, that's our starting thing. And each iteration of this loop, whatever this register is that has RSP plus 16, we're going to add 8 to it because we want to look at the next pointer. We're going to start at RSP plus 16, add 8 to it, add 8 to it. And we're going to do that 3 times because we pulled out of there. So we're going to do this until whatever that thing is that we pulled out of here and decremented by 1 until we compare that with 0 and it's 0, right? We're just sketching what this is going to look like in our heads, and then we're going to implement it. Let's implement it now. Puppy.s. Okay. And when we inevitably make a mistake, or maybe we won't make a mistake, but probably we're going to make a mistake, we're going to discover that mistake with GDB because I'm going to assume something and I'm going to think about it slightly wrong. We're going to see how I thought about it wrong with GDB. Okay. Let's do move. We want to grab straight out of RSP and throw that into a register. I'm going to use R10. R10 is a register. It's a cool register. We're going to use it. And what we're going to do is we're going to pull out of RSP. RSP, as we just showed in GDB looking at memory, is our argc. What did I say I wanted to do with this thing? I wanted to immediately sub R10 by 1. Okay, so it was 4. Pulled that 4 out of memory. It lives now in R10. And then we have a sub by 1, so now it's 3, if we think about that example we had before. Okay, we want to open a file, and then we're going to output all of the file. Oops. We're going to output the file, and we're going to do all of this stuff. And we jump to our while header. Right? We have this previous logic. What we want to do now is, well, let's think about the case. Hold on. How do I? Yeah, whatever. We'll keep rolling with it. Emacs is making me a little bit sad right now, but we'll roll with it. We want to think about the case. I mean, there's a number of ways to write this, right? The first thing that I'm going to do, though, is deal with the base case. We know we're about to write a loop. The loop is going to end as soon as R10 is 0. So compare R10 with 0. If R10 is 0, that means there's nothing to output. Now what we should do is jump to done. Right? We have our done label, exit 0, right? So right away, we check argc after decrementing it by 1. If it's 0, we're done. And this is about to be a loop. We'll call it our big loop. Okay, we're going to eventually jump back to this thing. Let's see here. Currently, actually, here's what we'll do. Instead of jumping to done, we're going to jump to exit, which currently doesn't exist. and we're going to rename, or we're going to add a bonus label here called exit. And we know right now, based on how we previously implemented this, I'm not even looking at the whole thing, but someone jumps to done when it's like done processing that one file. Instead, what we're going to do is jump our big loop. Is that what I call that thing? Our big loop. Okay, so someone jumps to done when it's done processing that file. Instead of exiting, we're just changing the logic. We're no longer going to exit. We're going to jump to our big loop. And our big loop is going to decide when we get to exit. Okay, this is how we're implementing it. But there's one thing I want to do before I jump to our big loop. I want to decrement R10, sub R10 1, okay? Because we're basically doing a for loop, right? Where you could think in C terms, I'm doing like for I equals 0, I less than argc minus 1, I plus plus, right? That sort of thing. This is what I need to do at the very end of my loop. When someone jumps to done, this thing that actually knows how to read a file, open the file, read the file, output the file. When it's done, it was jumping to done. And now what I want to do, decrement R10 by 1, jump to our big loop. If we only had one thing, R10 would have been 1. It would have compared against 0. We need to, there's an issue here. I said jump exit. This jump exit is not dealing with the compare, okay? Jump isn't using the results of the compare. I want to jump if equal, JE if exit, right? Otherwise, it just immediately exits. We see that in GDB, or we'll just fix it right now. Okay, compare R10 with 0. If it's equal, exit. Otherwise, go into our logic. Now, there's one more thing we're missing. Right in here, we are taking RSP, we're adding 16, we're pulling out of memory, right? That's what this right here is doing. This is always looking at argv1. Instead of looking at argv1, I want to look at the current argument. So I might need to add a little bit more. So you've written C before, you've written other programs. There's a million ways I could do this. In this case, we're just going to do the simplest thing that comes to mind. And we're going to basically have 2 trackers instead. We're going to, instead of adding 16, we're going to, move R11 16 and add R11. We could write this way more efficiently and not use so many registers and do math and stuff, but we're going to write this in the dumbest way possible. It's okay. This assignment does not ask you to write clean assembly. It asks you to write working assembly. Totally fine if you're being like inefficient with things. Add R11 to RDI. Okay, now there's just one more thing I need to do in this loop is add R11 8, right? So now I'm going to look at the next pointer and the next pointer and the next pointer and so on. And let's assemble it. So it assembled. We didn't have a syntax error, which is kind of nice. Let's just see if it works for our initial thing. Looks like it works for our initial thing. Does it work for no things and return 0? Yep. What if I say /flag/flag? Doesn't work. Darn, I was actually a little bit worried there that I was going to write this correctly on the first try. It doesn't work. This is a disaster. Now I have to debug things. This is your life. You get to debug things. This is the most important skill. First thing I'm going to do is strace it. What did I mess up? Can I see from the syscalls? Are all the syscalls working as I'd expect? And in fact, instead of flag, I'm going to do etc password here so that maybe it'll show up differently just in case I can see it with strace. Okay, so we open flag, which is what we'd expect. The very first system call we'd make is open flag. So we're handling that. We read, write, we read. And then look at this. strace is very helpful. It's so nice when strace is helpful. You don't have to figure out everything in GDB and strace tells you something. This is often going to be the case. We made a bad system call. Instead of opening etc password as we had hoped for, we opened 0x20,000. Very sad. And it complained bad. Okay, this means what we're going to hone in on, our control flow is like kind of correct. It's correctly going to an open next, which is nice. But for some reason, we're looking at the wrong thing. And so we're going to gdb copy start I flag etc password no display 8i RIP set disassembly flavor Intel. We are going to disassemble, where did we go? X100i RIP. I want to just set a breakpoint on this open. Okay, this open is right here. So actually, I'm going to start at the beginning of this open. So I'm going to break right here. And I'm going to continue to it, and then I'm going to continue to it again. So this is the first time it's opening the first file. If I continue, again, we're going to be looking at the second file. So for example, print R10, that was our tracker of how many things we have left to do. Print R11, well, this immediately looks not good. R11 is pointing at 20E, so whoever the heck is incrementing R11, right now I would expect R11 to contain 24, right? We initialized R10 or R11 to 16, but for some reason it's not pointing at 16 or 24, it's pointing at this weird thing. And so ultimately we'll see, ultimately we've got an issue, right? Something's going on wrong with R11. We also have another issue though. This is, actually, the real issue is we're out of time. So we will continue debugging this next week in class, or not next week, on Wednesday in class, and we'll figure out what's going on. If you want to think through what's going on, maybe you'll pre-figure it out. Debugging is going to be critical. We're going to go over debugging on Wednesday, continue our debugging, make our program work. Ultimately, this is your life now for this week. Thank you all for attending. Good luck and goodbye.